Hello everyone, my name is Tanner Harms, and today I'm going to be talking about some work that I've done with Professor Brunton and my advisor, Beverley McKeon. In particular, I'm going to be talking about finding Lagrangian coherent structures using sparse data, in particular sparse trajectory data. Let me begin by talking about how I might measure some fluid flow that I care about studying. Let's say we've got this flow around a cylinder here, and I want to study the vortex street that's evolving downstream. What I might do is I might try and envision an experiment where I can put a box around everything that I care about, just like this. Say that this is my whole experimental field of view and it encapsulates everything I want to study. In reality, this is not that practical. Typically, what I might end up with is something more like this, where the experimental field of view covers some of the things that I want to study, but there's a lot of interesting things happening outside of the domain that I'm actually able to see. So I could consider ways to fix this problem. One might be to take more cameras and more lenses and put more boxes over my flow, but this can, as you imagine, get expensive pretty quickly. So instead, what we're going to try and develop is some kind of tool to do mobile flow field measurements, where instead of looking at the entire box in its fixed position, we're going to take some structure that we care about, maybe a vortex like this, and we're going to allow it to move downstream and try and follow it with whatever we're measuring with. There are obviously a lot of technical challenges associated with this, and today we're going to talk about how we're going to try and address one of those challenges, in particular the challenge of objectivity. How do we measure something like this when our camera is moving at a different speed than the flow? That relative motion is going to change what I observe with my camera, and it means that I need to come up with ways of measuring things objectively so that regardless of my camera motion, I'm able to still identify the same structures. All right, let's talk a little bit more about this. Let's get technical with an equation. So I'm going to start by saying that this position x is our untransformed particle in some original frame of reference. And let's say that I'm moving my camera. This particle x tilde is now the position in a new frame of reference. And I'll only allow certain types of motion to happen on my camera. The first transformation that we allow is a rotation, and that's defined by this matrix Q. And we're also going to allow for translations defined by the vector P over here. Okay. So what this says is that we're going to say that any objective measurement is one that is the same in the transformed state as in the original frame of reference. So let's look at this in terms of an example. Once again, here's our cylinder flow. This time I'm also showing you the velocity in the streamwise direction. If it's red, that means the velocity is high. If it's blue, that means the velocity is low, or even negative in some cases here. What I'm going to do is I'm going to put a bunch of particles on top of this flow and let them move wherever the velocity field takes them. And then I'm going to watch those particles and see what happens. So here we go. We see that all these particles are moving in the flow. Some of them get caught in vortices. Some of them get caught right behind the cylinder. Others just move right along all the way out through the back of the domain. But because my camera is sitting here looking at the whole screen, I'm able to compute velocity fields that look something like this. But let's consider that case where we were thinking about before, where I'm not able to look at the entire field of view that I care about. Maybe all I can see is this box here. And maybe I don't have that much control over the thing that I'm observing with. So this box is subject to rotations and translations that maybe I'm not aware of. And so let's consider in the box on the right here what we would see inside this box here. I'm going to play the video, and we're going to consider what those two flows look like from their respective frames of reference. So if I'm looking at just the data in the box on the right, it might be hard to tell that I'm in the same flow as what I'm observing here in the lab fixed frame on the left. The rotation and the translation of the observer make it difficult to intuit the same information from the flow because of the relative position and velocity. Okay, this brings us to the subject of Lagrangian coherent structures. And here's an image that I think does a great job of elucidating this topic. This image was taken by a NASA satellite of an algae bloom off the coast of the Horn of Africa. These green streaks and swirls are the algae sitting on top of the water, acting as tracers. This is all part of the study of Lagrangian coherent structures, and if you're a fan of the channel, you've probably watched Steve's earlier video on the subject. He did a great job explaining what Lagrangian coherent structures are and how to compute them, among many other things, so I encourage you to go back and watch that, especially since a lot of what we're going to talk about for the rest of this talk are built up upon it. The other thing is, if you're interested in learning even more about this, you could go consider reading this book that was recently written by George Haller, which goes into a lot of depth on the subject. Professor Haller is an esteemed researcher in the field of Lagrangian coherent structures and has developed many of the analyses that come with the field. Okay, but in case you want a quick overview, I'm going to give a brief refresher. So if I'm computing Lagrangian coherent structures, I have to remember what space we're in. We're going to consider this physical space here, which is where the flow could exist at any time. And then if we look at it at one instance, we have a reference time here. Then if we look at it at some other time, we might have the observed frame. In each frame, we have a blob of fluid, and we're going to say that it's the same fluid in each part, but it's been deformed by the flow. The transformation that takes the fluid from this first time, the reference time, to the observed time is this function, is this flow map F. We're going to call F the flow map. If we're going to compute this, what we want to do is we want to take our velocity fields, which we have access to, and put a bunch of particles on top of those in a nice uniform grid like this. We're going to call this first thing the flow map from time 0 to itself. And then we're going to let them evolve to a future time at F from time 0 to some future time t. What we want to do is identify this linear operator called the flow map Jacobian, which transforms ft0 to t0 to its deformed counterpart f from t0 to t. It's essentially it's the gradient with respect to the initial conditions of the deformed position. Now, what this amounts to is essentially inscribing a circle around these particles here and watching it deform to some ellipse at the future time. This linear operator is only able to identify an ellipse here, so it's going to take all the particles that we used around this initial particle and fit an ellipse around them, and that's going to give us, essentially, this flow map Jacobian over here. Typically, that's done through the use of finite differences. But there's a caveat here, which is that it's very important that we use a small spacing in the grid here. Delta x0 between these spaces must be very small so that the nonlinearities of the flow don't ruin the results that we have. Let's take a deeper look at that. So I've got a cloud of particles here, and we're going to say that the initial spacing of that cloud of particles is pretty large. So as it evects through time, the nonlinearities of the flow affect it significantly so that we get this banana shape on the far side. If we try and fit an ellipse around that, we see that the ellipse doesn't really faithfully represent the actual deformation. And so when we do our analyses, we're actually misrepresenting the deformation and aren't able to make the same conclusions that we might if we had good access to deformation, if we had good access to very small spacing in our initial positions here. Let's look at this in terms of a video. Here I have a cloud of particles distributed by or colored based on how close they are to the center of the cloud. If they're red, they're really close, and if they're purple or pink, they're very far away. So we see that as they evolve through the flow, those particles that started far away from the center quickly deform in a very nonlinear way, spreading all across the domain. If I were to try and fit some kind of linear operator from their future positions to their original positions, I wouldn't represent the actual deformation of the flow well. But for example, the red particles and the orange particles, which started really close to the center, those do still have that linear deformation because they started really near to the initial condition that we cared about. Therefore, when I'm doing these LCS analyses, typically what I want is to have a very dense distribution of particles so that I can accurately compute my gradients and then my deformations. Now, when you're watching that video, one thing you might have noticed is that over short periods of time, the deformations were still pretty much linear for all of the particles. And so I can take this cloud of particles and look at all of the intermediate times as well and see that in this region here, we're still linear in time. And in the regions beyond that, the nonlinearities start to dominate. This brings us to the work that we've done on this subject, which is encapsulated in this topic of Lagrangian gradient regression. So we're looking at the cloud of data here. We have our initial time and our future time, and we'll call this x at ti and x at ti plus 1, and we want to fit the operator df between them. We're going to say that the two times are close together in the flow. To do this, we're going to use this equation up here. We want to solve for df, and for those of you that have followed the channel, this is a lot like what is done in the process of solving a dynamic mode decomposition or doing a DMD. What we're going to do is we're going to take the inverse of xti, which is a matrix, and often it's not a square matrix, so the inverse like this is not appropriate. Instead, we'll have to do the more Penrose pseudo-inverse to accomplish this operation here. We're going to go a little bit further and do what's called a kernel-weighted regression with regularization. And essentially what we're doing is we're taking the distances of particles from the particle that we're looking at within some radius, making a matrix of those differences. And then we're going to measure those distances at the deformed time, put those into our regression problem, and then we're going to weight them according to some kernel function. This function f is a kernel function, which assigns a weight to a weight based on the distance of particles from each other. And then we're going to populate this matrix K so that each particle is compared with every other particle. Sometimes what we might want to do is only look at the particle's distance to the center particle, in which case we'll get a diagonal matrix over here. That's typically what we end up doing that performs very well in practice. Okay, so we have this, we have our deformations here, and what you may have wondered throughout this is, okay, we have our time 0, and that has a linear deformation to time 1. That's great. But beyond that, it's nonlinear. What about from time 1 to time 2? Is that still linear? Well, it depends on which particles we use, but if we resample at each time, what we can do is we can say that this deformation is still linear, and then the next deformation is linear if we use new particles. So we'll throw out any particles at each time step that go too far away from the one that we're trying to observe. And then by using the composition property of these trajectories, we're able to compute the flow map Jacobian over arbitrary times by taking the product of all of the intermediate Jacobians. That's the first thing that we're able to do here, and that's identify Lagrangian coherent structures from sparse data. As it turns out, we can do more than that. We can actually compute velocity gradients from the flow map Jacobian without ever computing derivatives or finding fields of data. Or finding velocity fields, which can be very convenient in some cases. To talk about how well this works, we're going to use this double gyre flow again. And in particular, I'm going to talk about 3 metrics. The first one is planar vorticity, which is defined like this. We also want to look at the Finite-Time Lyapunov Exponent, which Steve talked more about in his video on Lagrangian coherent structures. This is essentially going to give you a measurement of the maximal stretching over the domain of observation. Finally, we'll look at something called the Lagrangian-Averaged Vorticity Deviation. And this is going to give you the accumulation of rotation throughout a particle's trajectory. It's going to tell you how many rotations that particle undergoes from time 0 to time t. Okay, let's start by looking at the vorticity. Here's our analytical result. And when we apply LGR to the problem, we get something like this. Let me talk a little bit about what I'm showing here. Each one of these is the vorticity field, but it's been interpolated from sparse particles, which I'm indicating as gray dots here. When I have 100 gray dots on the screen, that means I'm using 100 particles, and the space in between the particles is filled in through interpolation. All right, so when we use only 100 particles, we're still able to see the 2 important blobs of vorticity in the double gyre problem. As we go denser in particles, the comparison with the analytical result only improves. So even with very sparse data, we're still able to compute accurate velocity gradients without ever interpolating our velocities into velocity fields. The next thing to talk about is sparse FTLE fields. So here on the right is a baseline FTLE computation. It's been done using finite differences, which is the typical approach. I'm going to use 80,000 particles for this computation. Typically what I'm looking for in such an analysis are these red lines, these ridges of the FTLE field which move throughout the domain. if fluid starts on one side of those ridges, it will not go across the ridge to the other side of the domain. So it's very useful for determining things like barriers to flow transport, seeing where things mix and where they don't. All right, we also want to make a comparison of our methods to conventional methods. So the way that we're going to do this is, for the conventional approach, we're going to take our initial cloud of particles, which is determined by the nearest neighbors of whatever particle we're analyzing, and we're going to watch them and deform throughout the full time domain, and then we're going to look at the final time and perform our regression with the initial time. Then when we use Lagrangian gradient regression, we're going to use all of the intermediate stages along the way to compute our full Jacobian. Okay, here are the results. In the conventional approach, we can see that even with dense particles, we still don't do a good job of representing the structures of the FTLE field. The nonlinearities of the flow are just too much for this type of data. This is too sparse for using first and final times only. But when we use Lagrangian gradient regression, we're able to, even with 250 particles, identify where the important ridges in the field are. And as we get more dense, we only do a better job. Finally, we're going to look at the Lagrangian-Averaged Vorticity Deviation. In this field, we're trying to identify where the Lagrangian vortices are, and these are indicated by the large blue blobs on the field here. And once again, we're using 80,000 particles that are organized on a nice grid. When we do this in a sparse way, using Lagrangian gradient regression, we find that even with 100 particles, we're able to represent the vortices in the same places that we saw them in the analytical data with the same magnitude of values. And as we become more dense, as with FTLEs and the vorticity, we do a better job of representing the flow. So one thing that you might have noticed while we were looking at those results is that it's much easier to represent vortices in a sparse way than the Finite-Time Lyapunov Exponent ridges. And there's some intuitive explanations for that. Let's take a look at this schematic. So here on the blue, I'm trying to indicate that these are coherent vortices, Lagrangian vortices, as indicated by LAVD fields. And then this orange line that goes between them is some hyperbolic Lagrangian coherent structure, essentially an FTLE ridge that moves through the flow. In these vortices, we see that lots of particles are entrapped, and not only are they're enclosing some kind of volume, or they're covering some kind of volume, but they stay within this volume over the period of time because they're trapped in the vortex, so to speak. However, when you're looking at the FTLE ridge, particles will start close to it, and they'll spread apart. They'll move away from the ridge because FTLE ridges are by nature repelling. They push particles. Particles move normally away from FTLE ridges. Another thing that makes it difficult to identify these ridges in practice is that they're infinitesimally thin. So when I have only a couple particles near them, I'm not going to do a good job of representing the ridge well because I'll only calculate it at some finite and sparse locations. So it won't do a good job of capturing all of the features of the ridge because there's simply not enough data close to it. All right, the last thing that I'd like to talk about in relation to LGR is putting it to practice in actual experiments. So what I'm showing here is some data that we took in the lab of flow past a splitting plate. So essentially I've got a plate here that moves upstream in our water channel, a long ways back. And then on the top side here, I have flow that's moving slowly, and on the bottom, it's moving a little bit faster. The way I'm going to visualize this flow is by putting a bunch of wooden tracers in it. So I just dump a bunch of wooden spheres into it, and these are unconventional. Typically, if I'm doing a fluid flow measurement like this, I'm not going to use particles like wooden spheres because they're really difficult to detect, and then even if I can detect them, they're going to be far apart, and it's going to be hard to compute velocities or velocity fields and vorticity and all these different things. But using LGR, we're able to do that, and that's what I'm going to show here. So as I play the video, I'm going to color the particles with their vorticity as we computed it according to Lagrangian gradient regression. So here we see that at the trailing edge, particles on the bottom start to turn towards the trailing edge, causing an oscillating vortex street. This is exactly what we would expect from such a flow as this. On the bottom, because the flow is faster, the vortices end up becoming larger and pulling particles from the top surface down, which we can see. We also see that the vortices on the top surface are being pushed sort of upwards and to the right here in this side of the screen. The point of showing this is that this type of measurement is difficult to do if you don't have a tool like LGR to make sparse measurements from tracers like this. Normally you'd need a much denser distribution of tracers to study these. Anyway, that's all I've got for today. Thank you very much for watching the video. I hope that you enjoyed it. And if you're interested, please go check out those other resources.